In she goes.
And stuck.
Ooh.
I was watching a classic sci-fi film the other day in which doctors were put into a submarine and shrunk down to a teeny tiny level, and they were injected into a patient so that they could cure the disease. It inspired me to build this ship for Dr. Intrepid. In you go. But it also gave me a question. We've had this idea for decades, so where is it? Why can't we take machines and shrink them down to the nanoscale to inject into a patient to fight the disease? Well, Professor Stoyan Smoukov is a nanoengineer at Queen Mary University, London. I'm going to ask him that question now.
Dr. Smoukov, hey, thanks for having me. Nice to meet you.
How are you, Greg?
Good. Meet Dr. Intrepid. We're going to send her on a journey.
She's
Yeah, so
explorer.
she's a famous explorer. I don't know what she explored, but my current thinking is, could we get her to explore inside of somebody's arteries, say, or inside of somebody's body to go do something like fight cancers?
Yes, and I think that that's a great and underappreciated area, actually, of robotics, because, all the big robots that people have thought about, including all of these fantastic movies about Transformers, everybody assumes about big robots and how everything is made up of motors,
Propellers and
structures.
wings. Yeah.
Yes, but if you think about computers, how everything got miniaturized, and how everything is actually a lot more efficient if you have the processors and the memory just working on nanoscale.
This is a really interesting point. Early computers were huge, built from bulky vacuum tube switches. Miniaturization was only possible with the discovery of silicon transistors, which allows thousands of switches to fit onto a single tiny chip.
But if we try to make the same thing with robots, we can't use the same components we have today. We can't use the motors. We have to think of other ways of doing things. And perhaps one of the best ways that we've been working on in our lab is to start growing things from the bottom up. Just like we grow plants, just like we grow bacteria, why not grow robots?
I thought we were going to talk about traditional engineering, but just on a tiny scale, like a watchmaker. But growing robots is not what I had in mind.
Okay, so why can't we just take a robot like this, or a ship, and shrink it down? Why doesn't that work?
Well, for one thing, the principles that work when you have a big submarine and when you shrink things down, the same principles don't work anymore when you want to have movement.
Just because the fluid it's not different, it's just that the viscosity becomes more dominant at that level?
Yes. So different things scale in different ways. So yeah, viscosity is a huge problem. If this kind of large structure got immersed in a much more viscous medium.
It turns out these scaling effects have a big impact in the nano world. Viscosity is a fluid's resistance to flow. And water has a fairly low viscosity, so we don't think about it much. That's because we have enough mass that our inertial forces, i.e. those of movement, dominate the viscosity, so we can glide through the water when we swim. But if we were to become tiny, our inertia would decrease dramatically while the viscosity of the fluid around us would remain the same. So if we were shrunk to the size of, say, a bacterium, the water around us would feel very thick and gooey.
Well, we have a bunch of honey over there, and I can try to show you what that means.
All right.
If we have some water in this container, one could imagine how this will be able to kind of move fairly freely, and if you have fast enough rotation, you'll be able to actually move inside the water. But
so we're gonna pop her into honey here. In she goes.
and stuck.
And what I notice immediately is that it's just as hard in either direction. The streamlining doesn't seem to matter at all.
No, and that's a problem that a lot of bacteria and microorganisms have to deal with, how to move in media that seem as viscous as honey.
And it seems like it to them. And yeah, I noticed when I turn the prop, it actually, so it certainly doesn't push the honey backward. It literally crawls through it as it moves sideways. It turns the whole ship sideways. So it's like at that scale, you don't try to sort of use propulsion via any kind of, propeller. You would just literally kind of crawl your way through it.
So there are several different mechanisms that people could use when they're designing these kind of artificial swimmers. But yeah, certainly it's not about shrinking something large to be able to replicate it on the small scale.
She's going to eject to safety.
Well done.
Okay. Okay, so if we can't shrink what we think of as macro scale robots down, we have to start from the ground up. But where do you start thinking, from the ground up? Do you just invent this stuff at the top of your head?
Well, you can take a lot of inspiration from nature, and you hope sometimes to get lucky as well.
So like little natural mini robots?
For sure. And while that may sound really far-fetched in science fiction, actually a lot of micro and nano robots in fact exist all inside our bodies.
What Stoyan is talking about here are these amazing molecular robots that we actually have inside of our own cells. So, in our cells we have these things called vesicles, and they're full of molecular cargo that has to be transported from one part of the cell to the other. How does it get there? Well, inside of the cell are also these microtubules that are kind of a highway for the vesicles. How do these vesicles move along these? Well, they have these little proteins that look sort of like legs, made of kinesin. And through a repeated series of chemical reactions, these legs attach to and unattach to the microtubules, allowing them to walk on down the road.
That's a robot of sorts.
That is definitely a nanorobot inside us. It's just that we don't know how to make those artificially yet.
But we're
trying.
getting ideas, yeah.
Definitely.
And I guess that also works with flagella and the way that they move around, that we know that they spin by these nano-robots.
Sure. So for a lot of microorganisms like bacteria, you can have flagella. You can have ones that turn. And so you can have a helical type of turn in some very complicated mechanisms in bacteria, which have a gear inside it.
Yeah.
Flagella are common structures that many microorganisms use to move about. While they look whip-like, at the scale of bacteria, they actually operate much more like corkscrews, propelling the creatures forward or backward by drilling through the viscous environment. But how do you go about making something like flagella for nanobots?
There's a lot of exciting directions from here on. The question is really, can we go to nanoscale?
Okay.
And that is something that has been really exciting to me because we both have fundamental discoveries in this area, but also some practical applications. For example, in this secret container here from our lab, we have several types of emulsions. We have regular emulsions, and we have nano-emulsions that we have made with the same compositions.
Okay, so an emulsion is made up of two liquids that don't naturally mix with each other. But if you shake them up, you can get a suspension of tiny droplets, where one liquid is suspended within the other. I'm intrigued to see where this goes.
This first emulsion is a bit like milk.
Okay.
It has oil and water, just like milk, 1%.
Okay.
And then it's white because the droplets are small enough that you don't see the droplets, but they scatter the light.
Okay.
Just like milk.
They scatter every wavelength and it goes all over.
Because it scatters the light from the droplets.
Like a cloud.
Just like a cloud.
Okay.
But then we have just taken this emulsion and processed it several times with heating and cooling, only mildly heating and cooling several times, a couple of times in this case. And suddenly it becomes a lot more transparent here on the side of the black.
Yep, I can see that.
And then for the final round, 2 more times of heating and cooling, and we have really transparent emulsion with the same amount of oil.
And it's just heating and cooling.
Work? Just heating and cooling.
And so these are now so small that they're not refracting the light. The light's not interacting with them.
Exactly.
It's straight through them.
They're not only smaller than the wavelength of light, they're almost like 10 to 20 times smaller than the wavelength of light, so it's really not interacting with them.
Wow.
This is actually really cool. By a very simple process, Stoyan has made nanostructures in the form of tiny oil droplets. This could be one way of growing nanobots.
What can we do with them? We may be able to use these not only because they're transparent and they look cute like that, to deliver drugs, and deliver drugs very effectively in ways that our body can process them better.
So you can attach them to the drug or put the drug inside of them and then inject them in the person. Okay.
And this is much better than a lot of previous approaches of using drugs because we can load up a lot more drug, and yet we can also deliver them very efficiently inside tumors, which need to have very small particles in order to effectively go into the tumors.
Fantastic.
While this isn't the nanobot that I had in mind, this could help to fight cancer, and that would be a game changer. Stoyan makes it all sound so easy, I'm starting to get concerned.
Well, it's maybe not fair to call them nano-robots yet. You're working toward that. Should that worry me? Because when I think nanobots, immediately the sci-fi concept of gray goo, where if these bots learn to use the material around them, which they can chew up anything and turn it back into themselves, they then can replicate ad infinitum and they just take over the world.
Well,
I'm glad you laughed. That makes me a little less worried.
Yes, yes. That is a powerful image that I guess has scared in the last, 15, 20 years a lot of people, but it's something that I think we should not be so worried about. I think there's a lot of assumptions in doing something like that, where not only do you have these nanorobots, but they're actually very complicated and they're self-replicating. And guess what? A lot of these kind of nanorobots actually already exist inside us. Already we know that, for example, in living things, we have these kind of robots that don't cause these problems.
Right.
For example, the molecular machinery that transports molecules across the cell.
There are limits to what these type of robots can do, survive, gather resources.
Got it. And we shouldn't be too worried about building nanorobots because our body's full of them anyway, and they don't go ballistic and turn into every possible thing. Excellent. Well, thank you very much. And Dr. Intrepid by name, Dr. Intrepid by nature, thanks you as well. Doctor, looks like you've come to a sticky end.
I came into this with the question, why can't we take nanorobots and put them into a person's body to cure disease? Professor Smoukov has told us that because physics operates differently at the nanoscale, we cannot use the conventional approach that we would use for robotics. He thinks the key is following in nature's footsteps and growing robots from the ground up as opposed to shrinking them down. These robots may not defeat the Decepticons, but they may defeat a lot of cancers, and that is a sequel I'm excited to see. Until next time, remember that between the question and the answer are all the really tasty bits.
I was listening. It's real. I'm really listening. Hello, my baby. Hello, my honey. That's right, like this. Like this. Hello, my baby. Okay, like this. We'll try that one again. Yeah. Woo-hoo-hoo.